So the third model that I would like to study is the quadratic regression model. And we can do that again by going to Stat, moving over to Calc, coming down to number 5, right below the linear regression. A first-degree polynomial will be the quadratic regression, which essentially is a second-degree model. I go ahead and hit Enter. Yep, my independent variable, my dependent variable, all set. We're going to store this equation again by going to yvars and function, and we'll store it into y3. I'll go ahead and hit calculate, and you'll see that I get an A, a B, and a C. And if I just plug those numbers in the way you see it up in there in the template right over here, then you would be coming up with the following quadratic regression model of D equals 167.2629 times y squared minus 217.8416y plus 14,018.9789. Now, an interesting question is, I would normally have asked, is what's the correlation coefficient? The more important question is, does the quadratic regression model use a comparable correlation coefficient similar to linear and exponential? If we go back over to the screen, you will see that on the bottom, I see a r squared. I don't see an r, and more importantly, I also see a capital R squared. So I guess the answer is no. The quadratic regression uses this capital R squared. Linear and exponential regression models had an R squared, but it was lowercase, and we always just focused on this individual R itself. Given the quadratic regression model and its context, which value, A, B, or C, shares a familiar purpose? C. It's the y-intercept. And that's all we're going to worry about when it comes to quadratic regression models. And C in this problem is roughly 14,019, which is why we're going to use that to explain that the model predicts that businesses spent roughly $14,019 million on research and development expenditures in 1970, because we are going back to our independent variable. So, can we still predict with quadratic regression models? Sure you can. If you want to interpolate for the year 2004, then you're going to stick 34 into the equation. But notice that you have to plug it in twice. You have to plug it in where it says y squared, and then you have to plug it in to the linear term where it says y. And you'll come up with a prediction that's roughly $199,968 million. If you want to find the residual, back to 191,346 we go, subtract the 199,968 you just came up with, and come up with a residual of negative $8,622 million. If you want to predict for 1953, now you plug in the negative 17 into the quadratic and linear terms, and you'll come up with 66,061 million. If you want to predict the residual, 2247 minus 66,061 gives you a residual of negative $63,814 million. It seems strange that 1953 would have such a large negative number for a residual, but that will be better explained when we look at the graphs. So let's move on to predicting for the year 2025, which means plug 55 into the equation and come up with a value of $508,008 million. Find the year when roughly $600,000 million will be spent on research and development by businesses. If we're going to try to find the year closest to producing that kind of amount of money, set your quadratic regression model equal to 600,000. Since it's a quadratic equation, there are 4 methods that we can use to solve: factoring, graphing, completing the square, and the quadratic formula. Of the 4, only 2 seem most appropriate: graphing and the quadratic formula. In both cases, we need to make that equation equal to 0. To the calculator I go, where I type in 14,018.9789. I subtract 600,000, and I come up with a brand new constant, which I replace into my equation so that the equation now equals 0. If we're going to solve by graphing or by quadratic formula, both problems are going to produce 2 answers, and they're listed there. One will be negative 58.5415, the other one will be 59.8439. Let's show you how to, again, do both methods. First, the graphing. I go ahead, I hit Y1. I'm going to type in 167.2629. Can't put a Y, but I can put an X, and I'm going to go X squared. Minus 217.8416, and then I'm going to hit X. And then I'm going to go minus 585,981.02 0.211. And I've got that now entered into the calculator. I got to think about my window settings. Now, let's be honest. I see what my answers are supposed to be. I know I have to go to at least, negative 58 and 59. But I'm going to hypothetically think, let's just say I'm going to go back 75 years. So we'll put in 75 here. And I'll go ahead and say 75 years here. Now, the first thing that should come into mind is, why would I be going to the negatives? That's a good point. I expect my answers to be going down, but we're going to re-emphasize a point about graphing, parabolas. We'll go on to X scale. We'll just say we'll do this every 10. I have to get to at least, I have a y-intercept that's at least negative 585,000. I'm just going to go for down here, I'm going to go 1 million. And for my y max, I think I'm going to go 1 million. I don't think I need my y scales to go by ones. In fact, I think I'll just go 500,000 and keep it pretty simple. We're going to go ahead and hit graph. There's our parabola. I'm going to go ahead and hit second trace. We're looking for where the height becomes 0, known as also a root. We'll move the left bound past the point, which should be right there. I'll hit enter. We'll go past this point. We'll hit enter. And their guess is, well, right between there. So I'm just going to hit enter there. And you'll see that we got the first answer of negative 58.5415. When I go ahead and hit second calc, okay, so there it is, and I choose 0 again, I'm looking at this, and if I'm counting 10, 20, 30, 40, 50, 60, 70, I know my answer has to fall between 50 and 70. I could just literally put in 50. I could put in 70. You'll see it shows me my little bounded area, or bounded region would be probably better to say. And then I'm just going to go ahead and guess there, and I came up with 59.8439. All right, there's my two answers. What would happen if I wanted to solve by a quadratic formula? Well, I would need to remember it's going to be negative of a negative number, so negative 217.8416. So a negative of negative positive if you want to. I'm going to have to do this twice. Let's just start with the negative value, so minus the square root of, what we got here, now be again parentheses, we don't want to forget that, negative 217.8416 parentheses squared minus 4 times 167.2629 times negative, where's my negative? There's my negative, 585,981.0211. That's all inside parentheses, inside the radical, but now I have to use parentheses around the whole thing, and then divide this by 2 times 167.2629. Now, if you were to use the fraction features and make sure it look like the quadratic because you have math print, go for it. This is to help all students who have 83s and 84s. You hit enter, you got your first solution, negative 58.415. And the beautiful part is if I hit second enter, I can just go back over here and tweak the problem. So instead of saying I'm subtracting, I will add now. And I hit enter, and I come up with the second answer, 59.8439. But if I analyze my two answers, only one makes sense because it looks like it's increasing as it goes forward. So it makes sense that I would want the positive answer. Going back negative 58 years, I'm not expecting that 1912 we were spending $600,000 million, which is the same as $600 billion. That doesn't seem like a reasonable answer. So we're just going to focus on the 59.8439, which works out to be 60. And if you add 1970 by 60, it says that the quadratic model predicts it will be 2030 when we'll reach this particular amount. At this point, I'm back to asking myself again, how good was my extrapolation of 2025? How well does 2030 really do for predicting $600 million in research and development. So the best thing you can do is go back and look at our two different graphs. We go to the second stat plot. It's set. We go to the window. It's set. We go to y equals. We've got three equations. Linear's already turned off, but the exponential's not. Let's go over here and turn it off. We've got the quadratic because we had it automatically inputted in when it did its regression, and so we hit graph and we look at this. So do you remember an important property about parabolas? The direction of opening. This parabola happens to be going up. In this case, the right side really does a nice job fitting the data well. However, the parabola is also going to go up on the left side. It's going to increase. I would be expecting the numbers to be going down, like here in 1969. And if I go back to 1953, that would be about here, and that number was even lower, and yet the graph is now even higher. It's predicting a higher amount. That means my residuals are going to become more and more negative. Okay, so essentially, half the parabola will make a great model. The other half will make a very poor model. How would its residual plot look? All the residual dots are hovering around the x-axis, which means all the errors are small. They're all within 25,000 positively and negatively from their observed values. So from 1969 to 2018, this is by far the best predictor because we didn't have dots this close for linear. We didn't have dots this close to zero for exponential all the way through. So when asked which of the three regression models best fits the data, you can't talk about the correlation coefficient because linear and exponential uses R. Quadratic does not. We definitely need to say the quadratic model fits the best. And here's the phrase you want to remember when I ask you why. Because its residuals were closest to zero. It's as simple as that. Its residuals were closest to zero.